Yes, hello and good afternoon for those who are in Europe. Otherwise, good morning or good evening. Welcome. Apologies for the, let's say, few minutes delay, but we still have technical issues. My name is Federico Fieri. I am a senior scientist and also now expert on atmospheric science in EUMETSAT. I will guide you today in this second event of the data visualization workshop that is organized by EUMETSAT in cooperation with the support of the Copernicus program. Probably for those who have not been to the first event, the objective today is to have 1 hour and a half about of presentation and discussion, question and answer about data visualization, Earth observation data visualization with a specific focus on the thematic of air quality, wildfire dust. So everything is basically suspended and composing the air. I won't take additional time, but first of all, I want to introduce you my colleagues, the other panelists that are today with me. So firstly, in order of appearance, Cathy Clerbaux, that is a senior scientist from the National Research Council in France, and Cathy is, basically the best expert, or one of the best expert of the YASI instrument, and you will hear from Cathy that YASI provided a lot of insights in terms of scientific information, but also public and let's say citizens awareness impact. Mark Parrington, that has still some troubles in WebEx. Mark is a senior scientist at ECMWF, the European Center for Medium Range Weather Forecast, and is part of the CAMS program, that is the Copernicus Atmosphere Monitoring Service. And Mark works a lot on wildfire, on visualization, on data, and is also very, very active in terms of communication. You've probably heard about him in Twitter. We have Simon Proud. Simon is from the National Environment Research Council or National Center for Earth Observation in the UK. So welcome, Simon. He's a senior scientist and also a big expert in analysis of satellite data in many aspects. We will also have with us Julia Wagemann. That is Julia is a senior data scientist and works together with EUMETSAT and the other organization of data provider in MEEO, that is SME that is strongly specialized in data access and usage of Earth observation data. Then I will also would like to thank all the people that is supporting this webinar. That you will see around, and also Rosa that is putting in the chat information, and she will manage the question and answer. So please also take care and take a look to the chat where you will receive useful information. So if there are no additional points to add, I would like to start. So I will provide you an intro. So I will introduce myself, and I will provide you first intro on what we are talking today with some examples. Okay. Okay. So it will be it will be an introduction from myself and the first view on air quality and wildfire monitoring. Sorry. Again, this is a workshop that is organized by EUMETSAT with our partners in the implementation of the MEEO system that you have probably heard about, and is in the frame of the program of the European Union Copernicus. I start with the first image. This is the origin of the Earth images. This is 1946. This is taken from a rocket, and this is a sort of passage. At the end of the 40s, but also beginning of the 50s, there were many changes, very big changes in terms of Earth monitoring, in terms of atmospheric meteorology progress. Just think about about the meteorological year that was 1954. So this is really the moment where we start to look at our environment with different eyes. So with images, but also with a big push in terms of data. And basically from this, in the sector of composition and of air quality, of wildfire, we made very enormous steps. And this is basically probably now among the best or the state of the art observability. So here on the left side, you see an image that comes from the Sentinel-2 from Copernicus through the Sentinel Lab, and is provided by Pierre Marcuse. And you see that you have the possibility to observe both the plumes, but also the fire region and the burn area in one shot. And this one is something that you have also probably seen. This comes from the Sentinel-5P. That is the most recent satellite that has on board the Tropomi instrument and is provided by ESA. And this is an analysis that has been published just let's say a few weeks after the lockdown in 2020, and shows how the satellite can monitor the reduction in terms of the tropospheric column concentration that is related to the changes in emissions. And this satellite has an unprecedented resolution, geographic horizontal resolution, with the possibility to identify single emissive areas, like for instance towns, or like for instance also the ship routes that you can see here. Then we really made big steps, and these steps allowed us to make use of data sets, of products that can be used for many different tasks, or many different needs. So, for instance, we work with users, or you may have needs to work in communication. So to have impactful images, or images that have a strong uptake or a strong impact on the public. We do science, we need to do science, so we need to extract numbers, we need to extract quantitative information, and also we need to use satellite data, Earth observation data, and also visualization, representation of this data also for reports, for assessment, so for documents and analysis that have, for instance, an impact in policymakers. This is extremely important for quality, where in fact the Earth observation data are used and will be used as a support for the present and the future assessment. One important thing that we need to keep in mind is that we observe the intangible. No, sometimes we observe the intangible, because the pollutants, the gases are not visible with the eyes, so are outside the domain of the visible. And in fact, the satellite, the instruments on the satellite, they make use of different parts of the spectrum, of the electromagnetic spectrum that is observed by satellites, in order to retrieve and to estimate the number of molecules that are present in the atmosphere. And for instance, here we see that most of the species, the chemical species that compose the atmosphere, are not observable in the visible range that you can see here with this arc-en-ciel, this range from blue to red, that is the visible range. But you see that the different chemical species, or chemical compounds, they have an impact in terms of absorption. That is what we observe, in fact, from satellite in different ranges. For instance, in that case, in the infrared part of the spectrum, and I think Cathy will talk a lot about that. And then in that way, so working and analyzing in different parts of the spectrum, it is possible to retrieve the concentration of a large amount of chemical species. This again, here is the case of the nitrogen dioxide that is produced by combustion. So is related to the emission, for instance, from transport and from industry, and as you see here, is very well confined. Is very well confined around the town. So this is again from Tropomis 2018. This is the first month of observations, but also you have observation in that case, for instance, of carbon monoxide that is produced by less complete combustion. So the big sources are in that case both the anthropogenic but also wildfire. And you see here the retrieval of a global map. This comes from the YASI instrument that is on board the Method B, and that is one specific day with the different overpasses. And you see the presence of the strongest sources of wildfire. Yes, there is a question on concentration. I can take it just now. So concentration means the number of molecule per volume. So basically, when we discuss about a column, so imagine to have an area. So you have a column of air above this area, and this concentration means basically the number of molecules of a specific species, for instance, NO2, in this column divided by the volume of the column itself. And the column itself basically is the height of the atmosphere that we are sounding ratio the area. Okay, I see that there are other questions, but I will go to them. We will go to them in the first round of question and answer. Monitoring from space. I think it's important just to keep in mind that there are two different geometries we will talk about. The first one is the so-called low Earth orbit, and this is sun synchronous. So it means that you have the satellite that always orbit around the Earth and cover at the same solar time the same region. So it means that basically is peeling the surface of the Earth. So it has a repetition rate. So you don't have a continuous monitoring, but this goes at very high resolution. And you also have the geostationary. So basically you always observe the same face of the Earth, and then you have a representation MEEO-SAT-like, and this is the type of imagery that we can have. One important point is that it is then possible to monitor pollutants with satellite. And these again are two examples. So this is a global map of nitrogen dioxide, again from Tropomi, Sentinel-5P. And this is a map of ammonia from YASI. This is also to introduce what Cathy will talk about. Basically, NO2, as you see, is really related to traffic, to wildfire emissions, but also to combustion that happens at very small scale, like for instance, indoor fires, indoor combustion, and then accumulates in the regions of a higher concentration. So we have this image that is powerful, because I mean you really see which is the difference and where the most emissive area are. Also, ammonia is extremely impressive from my point of view, because production of ammonia is really related to intense farming, to intense cattle. And ammonia is extremely volatile and has a very, very small concentration. So you see that here we are really talking about a concentration that is order of magnitude up to 1 million concentration less with respect to nitrogen and oxygen. So there are just a few small molecules in a big volume, and accumulating the data for a sufficient long period, it is really possible to identify the regions where there are the highest emissions. And again, here you see many regions here, from the Indo-Gangetic Valley to the West Africa, to the Po Valley, to the emissive regions here in China, but also here in Kazakhstan and the north of Himalaya, where you have, for instance, really point emission, like probably Cathy will talk about one single plant of fertilizers. What does it mean to support, for instance, with the images and with the data, the assessments or science? So we needed to go from an image like this that already has numbers in. So these are concentration in a column. So this is micromole per square meter. While having, for instance, longer time series, you have the possibility to, for instance, to support, so to have information that is science, valuable, but also protocol or emission control valuable. This is, for instance, the change in ammonia concentration I think is in 7 years. This is in the region of Africa, and comes from a scientific paper from the YASI team. And you see, for instance, that you have an increase in ammonia, for instance, in the region of West Africa, and it is possible, for instance, to derive a trend, but also, for instance, to correlate or to analyze whether the changes in ammonia are related, for instance, to changes in the bird areas of the vegetation. So you can use Earth observation also to attribute, for instance, why there are changes, this type of changes in ammonia. And as you see here, for instance, there is a change in burned area here that is related, for instance, to increase in ammonia concentrations. Same thing, you can do it, for instance, for nitrogen dioxide. So you see here, for instance, the maps of nitrogen dioxide. This is during winter and this is during summer, with a very strong activity here in that case over Central Africa, due to wildfire. And again, here you see the difference, the changes in during the last 12 years. So you see that there are regions where you have an increase in nitrogen dioxide, possibly also related to an increase in pollution, and there are regions where we have a decrease. And for instance, again, the imagery and the satellite data can come to help and indicate, for instance, that the decrease in nitrogen dioxide is not necessarily related to a decrease of anthropogenic pollution, but is related in that case to a decrease in the wildfire activity, so in the emission that are due to the wildfire. So this is a typical application example. Again, here is a paper in PNAS where we can go from the images, so from the data to a quantitative information. We have many types of satellite. No? We have many types of satellite, many types of observation, many types of variable. And for instance, if you look at and you make Earth observation monitoring satellite wildfire European Space Agency, that is one of the implementers. Fortunately, ESA couldn't join today at last minute basis. But I mean, we want to represent also what ESA is doing. You obtain all these images, all these imagery. So you can see that you have, for instance, concentration of pollutants here. You see plumes. You see changes in the vegetation. Again, you see plumes. Here you see, for instance, carbon monoxide, but also more complex compounds like formaldehyde and so on. So there are many sensors that can observe the same phenomena in different way, providing different imagery and a different representation of the same thing. Now I will focus a little bit on the point of the wildfire, where we know, this is an emerging phenomenon, at least at our latitudes in Europe, is increasing the impact of wildfire, and has a very strong coverage and very strong interest from the citizens, but has also very strong impact in terms also of security, especially in the most populated area. And these are numbers, no? Some figures about the fires. So basically, the number of hectares that are burned, the amount of emissions, and also the fact that you have fires that are emerging in regions where wildfire activities was not so active in the last decades, like for instance the Arctic, that now is becoming a region where wildfire activity is becoming intense, even starting quite early, like this year. So we had, for instance, the first important widespread wildfires happening, for instance, in Canada and in Siberia, starting at the beginning of May. And in fact, one of the points is really to go from the image to the amount of tons, so to the mass of carbon dioxide that, for instance, is emitted by these fires in the Arctic, and that this is done, for instance, by the SCAMS system. Wildfire, they also have a strong impact in terms of climate, and is crucial because there is a change in the current and the future fire regime, with possibly prolonged fire seasons, but also with the changes in the burnt area. That is not even, that is, there are big difference among among the different parts of the world. These are three elements. So the first one here is this comes from the C3S, so the Copernicus Climate Change Service, and this is a change in ground temperature in Siberia, and you see in red that these are the regions where there were, during an intense wildfire season, very intense positive temperature anomalies. So basically, climate change and climate forcing. Here is an imagery from Sentinel-3 of wildfire in 2020 in Australia that were extremely intense, and you really see an enormous amount of small plumes that at the end build up a particle deck. This is visible, and this is, for instance, is the change in vegetated area and burned area. And you see, for instance, that here in sub-Saharan Africa, you have a different trend. So basically, you have revegetation with possibly also better control of the wildfire. So basically, the burnt area is changing in different way in different places. So again, imagery is extremely important to survey what happens, but advanced analysis of Earth observation is really crucial, for instance, to provide global long-term coverage, high resolution, and understand bridging the scales, because at the end the fires happens at a small scale but have an impact that is on the global one. I will probably jump this. Another way to observe fires is to observe the fire point themselves, and this is a variable that is called the fire radiative power. Basically, the fires are hot, and then you can observe when a fire happens, and then it is possible from the satellite observation to derive the fire intensity. This is in terms of megawatt. So the redder, the hotter, the more intense. And this is an observation that happens from geostationary satellites. So it is really the possibility to have a snapshot on where the fires are active in a certain moment. And as we have mentioned before, the satellite, the Earth observation, and the derived Earth observation products, they really help in the whole life cycle of wildfire. Here, for instance, there is an observation of the what we call the scars, the 5 scars, so the burned areas. And this is another intense season that happened in 2017 in Portugal, with the impact of June 2007, and the late season fires in October 2017 here that have an impact in terms of area that is comparable with the surface of a country like Portugal. And in fact, the satellite imagery correspond to an impact at the surface that really changes the color and really changes the status of the vegetation, as you see here. Okay. The same fire, and here now is an example of 2021 August in Greece, can be observed by satellite, and you can have very different visual representation of it. So the first one is when the fire happens, and that is again is the fire radiative power. So with the pixel that represent where a fire is active. Then you can make use of Sentinel-2, for instance, so with imagery at very high resolution. And again, this is again credit from Pierre Marcuse, with the specific balancing of the different channels. You can observe both the smoke plume, but also the burned area and the fire front. This is an image from Sentinel-3 of the same event. This is, I think, is here in the southwest of Turkey, with very intense fire plumes that are really visible from the top and really change the visibility. Then you can also have a bit fainter fire plumes, and this is during the same season, the fire from Eubea. And again here, these are particles that are not visible by the human eye, but can be detected in the ultraviolet. And you see that, for instance, the fires have an impact not only in the emission region, but in terms of plume that are advected and transported. And again, we can go ahead and look at in terms of atmospheric compounds. So this is carbon dioxide that, as we say, it is produced by burning, and you see that you have emissions here, here, and here that are really related, and here also in the southernmost part of Calabria. This is again the same period, so early August 2021, and you see that this carbon monoxide is produced by the fire. And then again on the same event, here you can see in the Euboea region, again in Greece, that is here where the fire has happened. Here is still green, while after the fire you see it as brown. So you have a drastic change in vegetation. And then it is entering what we call a data chain, and Mark, I'm sure we will talk about the CAMS service, the CAMS system, make use, assimilate the data, and produce, has the possibility to produce, starting from observation, merging with the model, for instance, to provide an estimate of the emissions and also the evolution during one season of the fire radiative power, so the amount of energy that is produced by fire. Again, this is the same event. We can see it in different ways. I just focus here on the nitrogen dioxide, again Sentinel-FSP, that with a very high resolution give really the possibility to see the effect of emissions. So the accumulation of NO2 from different emissive points, and you see here very clearly the presence of the plume that is related in that case to the fires in Antalya, again during the same season in 2021 in southern Mediterranean. And this is very well correlated with the smoke that is also seen as a visible image, and also carbon monoxide. It's interesting also that you can see in that case very high values of nitrogen dioxide related in that case to pollution, to very intense polluted areas. That is not visible here, for instance, in the visible imagery, because I mean there is not intense smoke, and that this pollution is gaseous pollution. I move to the end of my presentation, but I also want to tell you and to show you how you can put together different type of satellite imagery and satellite data to tell a story, no, about the impact of long-range transport. So again, this is tropomi, and that these are aerosols, so particles that are in the air, and that this is an example of the horizontal extent of intense wildfire in Canada, and you see this plume that is strained by the atmospheric circulation, so by the interplay of winds in the middle troposphere, taking the shape of a very well-defined plume. And that these plumes in some cases can go very up high in the atmosphere, also depending on the intensity of the fire that is pushing up in the atmosphere the smoke itself. And this is again the story that we have shown a few slides before. This is the Australia bushfire smoke, and these are satellites. This one is a Calypso, that is a LiDAR that is measuring from satellite, and has the possibility, for instance, to identify the height, no, of the aerosol. And you have this type of images. So the redder means that the stronger is the signal, so potentially the higher is the aerosol burden, and you really see that the plume that is of aerosol that is produced by the fire is rising up in the atmosphere up to 30-kilometer height in about 2 months, with a decrease in the color, and then with a decrease of the amount of the aerosol burden. And again, here you can also observe not the smoke, but the carbon monoxide that was produced by the fire, and you see that the carbon monoxide goes up in the atmosphere due to the larger scale atmospheric circulation. And again here, this is a snapshot. You see this this large smoke plume that is floating at about 20 to 25 kilometer height here above Chile. And again, this is a few days after the Australian wildfire event. Basically, the conclusion then is that we have a very, very strong and very unique chance to make use of many different types of satellite observation to monitor, in that case, not only wildfire, but also air quality. And just to tell you something that we're very proud of in EUMETSAT are the new images from the MEEO third generation that is now measuring the atmosphere at an unprecedented resolution with the order of 1 kilometer. So 1 kilometer really means what happens in that case at the scale of the single fire. And this is how a wildfire that has happened this year, 18/03/2023, so 3 months after the launch of MTG, and this is Fieri, so is the MEEO second generation. So you see the dimension of the pixel, and this event happened here at the center of Africa, and this is how the FCI, that is the new instrument that is on the third generation, observe the same fire. And you really see that you start to have the possibility to see structure in the same event. So it's just changing the glasses, no? It's just using a new magnifying glasses. It's not like the revolution of the Hubble telescope, but we are really going towards an era where we really try and we really push on the capability to observe at the more and more local scale. And here is an animation for 1 day showing the presence of the small fire events that you see as these small flashes, orange flashes, with really the possibility to detect fires happening at a very small scale. And I do it for a third round, also in order to show you here the possibility. You see it here, and on the top right, also the presence of plumes that are associated with the single fire events. This has a very big interest because one of the big point is really to be able to go from the sky, what you observe from the sky, to the needs at the ground. And the needs at the ground are really to go at the human scale, and the objective is really to bridge more and more this gap. I stop here. I took probably too much time already, but I want to thank you for your attention, and I stop my sharing. I invite you, as you have seen in the chat, to drop your question on Slido. We will have a Q&A session, and I just leave the floor to Cathy Clerbaux for the next talk. Please, Cathy, the floor is yours.
Okay. Share my slide. Hi, everyone. Up. Going on the top. Sorry.
Okay. Now we see it.
Okay, I'm going at the beginning. Yeah. Sorry. Okay, projection mode. Okay, sorry, that's not the beginning. Okay, hi everyone. So I'm going to talk about a satellite mission called YASI, and I'm going to give you some examples of what we see for fires and also for the ammonia detection that Federico nicely introduced. As also was said by the previous speaker, with infrared remote sensing, that is not what we see. This is a typical image of fires, and here you see the plume that is traveling with the winds. And we don't see that with the infrared instrument. What we see is what you have on the right-hand side. It's what we call an atmospheric spectra. It is basically the infrared radiation that is emitted by the Earth. And on top of that, you have all the signature of molecules that absorbed in the infrared spectral range. So I'll come back to that. And we have that for millions of measurements per day, which means we have to develop specific calculation, what we call retrieval algorithm, to try to retrieve concentration of gases that are in the atmosphere at the location of the satellite measurements. And of course, we have some efficient way to do that, like neural networks or any efficient way that exists, in order to try to do that in near real time, because we have millions of measurements per day. So the Yaji instrument is flying on board a satellite that is called METOP, and that there has been 3 METOP flying. There are 2 that are still alive. And this instrument initially was designed to help for weather forecasting. And it has also great capability to measure trace gases, and that's what we perform with our team here at LATMOS. And that allows us to follow several stuff, natural events like fires or volcanic eruption, for example, but also pollution coming from different sources. And I'll focus, in fact, on pollution that is coming from animal farming or spreading of fertilizers. Okay, just to give you a glimpse of what the mission does, this is the Yazi instrument. It's a cubical instrument, 1 meter by 1 meter by 1 meter, and it flies on board the METOP satellite, as I said, and it's scanning the atmosphere, as what you see with this pattern. And we have all the location on the Earth that are measured 1 time in the morning, 1 time in the evening. And it's possible because it's an infrared instrument, so it's seeing during the night. And there were 3 launched for 3 different METOPs. The first one has been discovered 1.5 years ago. And what it does, it records the infrared emission by the Earth. So the source of the radiation is the Earth. And what we see with the detectors of the instrument is, in fact, the composition of the atmosphere. So this is a typical Yazi spectra, and what we see is really the fingerprint of all the molecules that are absorbed in the infrared. So the main molecule is water vapor in the middle of this plot here, and we have also all the climate gases like CO2, methane, N2O, for example, ozone. And we have also some gas that are more reactive in the atmosphere. I'm going to show you some example with this guy here, carbon monoxide. And this one has a lifetime that can span between 1 month and 3 months. And that's a very good candidate to follow plumes, fire plumes, in fact, because it can really travel with the wind and it can go away, but not too far, because it only lasts in the atmosphere for a few months. Okay, so the first of my example is how we can track fires, and there are several gases that are emitted by fires, but here I'll focus on carbon monoxide. You know, when you have detectors in your home that are beeping if there is a fire, so it's basically based on carbon monoxide. So it's a very good way to follow fire plumes, in fact. This is again my Yazi spectra with all the molecules that are absorbing. Here we only focus on that one. And what we derive for 1 day of observation, for example, this is a typical map. I think Federico showed one very similar. Here it was a few days ago. So here you see all the fires that are occurring at the moment coming from Canada, and what they do, they are transported by winds, in fact, and they can even cross the ocean, the Atlantic Ocean. So on this map and all the maps that I will be showing to you, you have the scale that here, what means a lot of CO is in red and less CO is with the different colors. And as you will see next, we can improve, in fact, the visualization of these maps by changing this color. And one of you asked in the chat, what are the units? And basically, as Federico also explained, it's what we call total column concentration. It's everything that the satellite sees in a column. It means from the surface of the Earth to the satellite, but it's basically until the top of the atmosphere. And we have like all the gas that is absorbing there is providing a signal. If we do the same exercise, but we average over a month, we get a much nicer map. And why? Because there are some gaps here in the first map. It's because of the track of the satellite, but you see also all these big gaps that are due to clouds. In fact, it's easy to understand. When the satellite overpasses a cloud, it cannot see under the clouds. And so basically, each time there is a cloud, we have no signals. But if you average over months, like in the second plot I show you, then most of these gaps disappear because the clouds are moving. And so if you don't get any data on the first day, you get them on the next day, for example. There are still some missing dots here. It's because we put a filter because there were some issues with the desert, Sahara Desert, where there's a lot of emissivity problems. So I took this map just to give you an example that we can still put some filter for data that we think can have large errors, for example. But what you see on this map is basically all the carbon monoxide that was seen during the months of April, the last April. And basically, there are a lot of sources located in China. It's because they still, it's the end of the winter, and they have a lot of heating system based on coal, and there's a lot of pollution there, and it's spreading, and it's spreading with the wind, so it's leaving China, and it's crossing the Pacific Ocean to reach, in fact, the US coast. There are some other large fires that are occurring now in Africa, like during all the year, it's moving around with the wet and dry seasons. Okay, then we can focus on some events. Here, it's the same color scale, and this animation is a loop, so it will start again. And here you see a comparison between, on top, it's a pretty clean year. It's a normal year, I would say. This is 2014. And the year after was an El Nino year, probably like what we expect this year. And you can compare the two. So what I would say, normal fires are during the September, October, November months. You have very large fires that are occurring every year in Africa, in Amazonia, and also in Indonesia. And sometimes these fires get crazy. For example, on 2015, it was so dry and the air was so hot because of this El Nino event that there were a lot of spreading of the fires all around Indonesia. And you can see that there were much more smoke this year than when compared to the previous year. Okay, let's now check another event, Australia. For this one, we changed the color scale because it was not easy to see something with the usual color scale that we use. So what we did, in fact, we put darker, like more purplish color when there were high level of CO, and we put 0 when there's a background level of CO. There's CO everywhere on the globe all the time, but in fact, we filtered the background. So when the CO is very low, we put a transparent color so that we can see more when it's an extra plume of pollution added by the fires. And here you have Australia is located on top on the plot here. And what you see is that in a few days, the plumes, the fire plumes have circled the whole globe, in fact. See, it's an average over 3 days, so that you can really see how it's transported by the winds. And on the second plot, you see it's going further, and then it's really coming back from where it was emitted on the third plot. And here, altogether, you have 10 days. And so in 10 days, it means that it has circled the globe totally, in fact. And it's passing, you see that there's some plumes that are touching the Antarctica continent. And that was, in fact, confirmed by local measurements, where they saw, in fact, that the snow was darker because of particles that were carried also here by the winds. And my last example of fires is about the California fires. Those are enormous fires that have occurred for 2 summers in a row. And here you see California, same color code as just before. Here you see a very large plume. We have also removed the background so that we can see how it's traveling across the ocean. And you will see it lasts for days and days, even weeks. There's a very large here. And then these plumes are crossing the ocean. And you can measure, for example, look at this one. This is a huge one. And we can really see them when we have, for example, an instrument that is located on the roof of my university here downtown in Paris. And for this even, in fact, we could see excess of CO, measure it with this instrument inside Paris. And this CO is coming from the fires. And we know that because we see the satellite patterns and we can follow those patterns with the wind. Okay, that was my first example. And now I'm skipping to another species. So just to let you know, I could speak the whole day, but of course I had to make some choice. So I decided to focus on two molecules, carbon monoxide, which I just showed, and also ammonia. So this is my second part of the talk. So ammonia came really as a surprise because it was not expected that we could ever measure ammonia by satellite. And why? Because it has a very short lifetime. It's not like with CO that you saw that could be transported with fires. Here with ammonia, we have very low concentration and they stay very close to the where they are emitted because they only stay in the atmosphere for less than 1 day. Usually it's hours and less than 1 day. It means that it stays very close to the sources. And so at first we didn't know what it is. So basically these are the signature that we saw when we zoomed on 1 atmospheric spectra, the red little stuff that you saw here. So luckily for us, we have a database from where we can where people collected data that are obtained in laboratories. And from that, we could guess it is ammonia that we see. That is one of the very first map that we saw. So on this map, you have a visible map, and we have just put in red where we observed ammonia. So contrarily to carbon monoxide, we don't see it everywhere all the time. We see it only on specific occasion or specific location. And at first we couldn't guess what that was, because usually we expect to have high level of gases, for example, over cities where there are some pollutants due to heavy car traffic. And here you see the maximum point where not over the cities. It's on the Netherlands, somewhere, but not in Madrid, for example, somewhere in Spain. Here it's the Po Valley, the Nile Delta. And when we made the connection by identifying what these lines here, we realized it's really linked to agriculture, both animal farming or spreading of fertilizer. Okay, thanks to that, we got the cover of Nature Geoscience magazine, which was really great. Why do we care so much about ammonia? It's because it's a precursor of particle, which means it's one of the species that will decompose into particles. And in Paris, when you are in Paris in the spring, this is typical view that you could have. You barely see the Eiffel Tower. And in spring, there is the accumulation of the conjunction of three things that provides particles. There is the usual car traffic. There are a lot of cars inside Paris. There is some heating system are still working because it's the end of the winter. And also there are the spreading of the fertilizer all on the fields all around Paris. And this is like on top of these three stuff, it's you have, if the weather is with no rain, no wind, you have this typical pollution even that can develop. So it's very important regarding to that, to be able to prevent them, and to be able to prevent them, we need to measure, in fact, all the sources. And we can measure, in fact, using the satellite, we can measure the source of ammonia. And how do we do that? For example, this is a typical YASI measurements. Here I took the Nile Delta as an example because it's easier to explain here. But this is 1 day of observation. And what we do, we do a smart averaging of the data, so we can increase, in fact, the reliability of the data. And this is important for ammonia because the signature of the molecule is so tiny that there is a lot of noise in the measurements. And so we need to have better data. So we average over a few days. That's what I'm going to show you. This is, for example, a week of averaging, and you start to guess that the Nile Delta is a place where there are a lot of fertilizing activity and farming and so on. This is a month. You see better and better. This is a year of data, and this is 10 years of data. And here you see everything that's emitting ammonia. Every little yellow or red dot corresponds to something that is emitting ammonia. And we did that for all locations on the Earth, everywhere. And there's this guy called Martin who did that during more than a year, in fact. He averaged the data, and each time he was trying to find an explanation on why there is an increase of ammonia in that location. And that's what he did. And this map is available, by the way. Okay, I'll focus on two of these little dots to try to convince you that we did a very serious job in that. This one here on the corner of Colorado and Wyoming, and this one here in Uzbekistan. Okay, the first one, let's see here, this little dot here. That's what we have with the Yazzie ammonia map. And then we zoom again, and we try to guess what this red spot is. And we see here that there are some fields, for example. When we get closer, we see this pattern appearing. And in fact, it's thousands and thousands of codes that you see from this Google Earth image. And so for each of these little dots, we did that exercise. And each time we had an explanation on why there is a source of ammonia under the Yazzie measurements. Let's see another one. Here, let's have a look at this red spot here. Zoom again. And here what we start to see is a huge factory of fertilizers, in fact, that is in Uzbekistan, Fergana Valley, in fact. There's a big industry of fertilizer. And there was only one tiny spot where we couldn't find any explanation, and it took us months to understand. And then this tiny spot is somewhere here in Lake Natron in Tanzania. And in fact, we proved, in fact, it was due to pink flamingo that were coming back every year at the same location. And in fact, you know that the ejection of these animals, in fact, they release a lot of ammonia. Okay, and all the maps, you could do that by yourself because the map is available online. If you just type Yazzie ammonia, you should directly fall on this map. Yazzie NH3, you directly fall on that. You can zoom, and you will see it shows like I just did for two of them. And we have classified them. So there's a color code you see here, agriculture, fertilizer industry, and so on and so on. And we have this color code for all the sources. Okay, we also have a collection of nice images somewhere on the IRIS website. You can just type IRIS Yazzie and you will find all these maps. Some of them I showed you, some of them I didn't because I had no time. And that's it. And I guess the questions are coming later, I don't know. Thank you.
Thank you very much, Cathy. That was, just great. It's is what we discussed before. So really going from the space, arriving really at the human dimension. So I see that there are many questions. So we will go through them in the Q&A. That will be just after the presentation from Mark Parrington, right? So I don't know, Mark, if you're around and if you are able to start. You see in the chat there are many greetings on Cathy and on the imagery. Mark, hi Mark.
Hi,
So I reintroduce Mark. I mean, you see at Mark's shoulders, there is a logo from ECMWF. I don't know if you can just switch a little bit. Okay, here is it. And yeah, Mark is a senior scientist at the European Center for Medium Weather Range Forecast. And he's one of the senior scientists of the CAMS service, that is Copernicus Atmosphere Monitoring Service. So I leave the floor to Mark, that will provide some thoughts and some concrete elements in bringing the information that we have discussed until now with Cathy to the public. Please, Mark, the floor is yours.
Okay, thanks, Federico. So can I just ask, can you see my slides in full screen mode?
Perfect. It's
okay, great. Thank you. Okay, yeah, so thanks to Federico and thanks to Cathy. Hopefully I'm going to build on what they've already shown us today, with some aspects of what we do with Earth observation data in the Copernicus Atmosphere Monitoring Service, and some of the visualizations around that, and some of the storytelling that we can do with our data products and with other data products as well. So I'm going to start with a bit of background. There we go. So in CAMS, so Copernicus Atmosphere Monitoring Service, or CAMS, so we're merging Earth observation data with models to then provide information on the state of the atmosphere in terms of composition. So this is air quality, greenhouse gases. We have information on emissions. We're looking at the global scale, but also the European scale. And we have various tools for looking at the impacts of emissions reductions, for example, where pollution comes from, what it means in terms of assessing air quality and the quality of the air that we breathe. And then these various downstream users, which are industry, government, policymakers, app developers, which take our products and put them into a form in, say, your mobile phone app. So that this data is accessible to many people to be able to plan their days ahead. And what I'll talk about over the next couple of minutes is just a bit of background of how we use this Earth observation data, and what it is that we're doing that's different to what we've already seen from Cathy and Federico. So this service element, that was mentioned earlier. So I'm going to start off with what is actually quite an old image now, and this is a Sentinel-5P image looking at NO2, so total column nitrogen dioxide, tropospheric column nitrogen dioxide over parts of Eastern Europe. So you can see in the blue sort of background values, and then in the red the cities standing out. So you can pick out Budapest and Vienna and Belgrade, and so we know and we've seen that Sentinel-5P is really high resolution, really helps us to pick out pollution hotspots in terms of the NO2 in this case. However, you can see from this image a lot of areas which are shaded black, and that's where there's data missing for the reasons that have been given, so cloud or artifacts in the retrievals. And so while these observations are essential, indeed we wouldn't be able to run our service without Earth observation data, the direct use of them can be quite limited because there are these gaps in space and time, and the observed quantities, generally they're the bulk quantities in the atmosphere, so total column or aerosol optical depth. And while it reflects what's happening in terms of surface air quality, it may not be exactly that. The satellites are not observing directly air quality. They're observing the loading of the molecules or particulate matter in the atmosphere, which is linked to what's going on at the surface, but it's not a direct measure. And as we've seen, there are numerous satellites with numerous different instruments measuring in different parts of the electromagnetic spectrum. And so the actual application of all of those data sets is quite daunting. It's terabytes of data. And so what we do in CAMS is we take those observations, blend them with our model, both satellite, as we've been referring to, but also non-satellite, so in situ aircraft balloon measurements, to provide a consistent 3D state of atmospheric composition. And by doing that, we're then able to provide forecasts a few days ahead, and also reanalysis of many years of data in a cell-consistent way that reduces the need to download multiple satellite data sets to be able to look at how atmospheric composition is changing. And one way of thinking about this is that we don't have the orbit swath information that's interpolated, integrated into our models, and we're providing essentially maps without gaps, if you like to think of it that way. And so just a final slide, just to sort of illustrate our workflow and how we do this kind of in practice, how we build and develop this and deliver this operational service. Going from left to right, we have our Earth observation data, so Sentinels, but various NASA satellites and other space agencies, and in situ measurements, so from regulatory research networks. They go into our global model. So at ECMWF, we run the IFS at 40 kilometers for most of our atmospheric composition. And this also feeds an ensemble, and there's a mistake here. I apologize, rather than 9 members, this is now an 11-member ensemble of European air quality models, which assimilate the ground-based observation as well as having the information from the Earth observation side. And then there's some examples here on the right of different users. So from policy products to mobile phone apps, as I already mentioned, and also there's some use of our forecasts for broadcasting and reporting air quality conditions around the world through television broadcasts as well. So let's have a look at what this means in practice. And I'm just going to start off with an animation which shows analyses of carbon monoxide. And this is carbon monoxide concentration at an altitude of 850 hectopascals, which is about 1.5 kilometers above sea level. And as we heard from Cathy, carbon monoxide comes from incomplete combustion. It's a very good tracer of atmospheric pollution because it has a photochemical lifetime of about a month, a little bit more. And so what that means is when it's put into the atmosphere, you can really trace where that pollution goes to, and even trace it between continents and at the hemispheric scale and the global scale. And so this animation is analyses, which is then this assimilation of the Earth observation data into the model to then provide this consistent, seamless state of the atmosphere. And also, I alluded to, this is using observations made at infrared wavelengths such as IASI, but also the near infrared and UV visible of the TROPOMI instrument as well. And so what it shows from the beginning of May up till yesterday, the transport of carbon monoxide particularly from those fires in North America, in Canada, also in Eurasia, and then various high levels of pollution around Southeast Asia. There've been fires in Mexico and Central America, so we see that plume, and then also the fires in tropical Africa, which are moving from northern tropical Africa to southern tropical Africa. So this really shows the interconnectivity of the world through the atmosphere and through atmospheric composition. I'm going to go through a couple of examples. I'm going to start by looking at the information we provide on wildfire emissions and how we've used that to visualize and also to try and to tell stories and connect together a bigger picture of what's happening when we're monitoring wildfires around the world. So there's some details on the right, which I won't go through, of what we're providing in terms of fire emissions and how those are produced. So Federico introduced the concept of fire radiative power. So we're using those kind of measurements. And then by applying information that we know about the vegetation types and the emission factors, we can estimate emissions of aerosols and trace gases and different pollutants. We currently have listed about 40 from our global fire simulation system. And so just the very first, very simple visualization is looking at the global distribution of fire radiative power for the month of May, for the current month. So this gives us a snapshot of the last 3 weeks or so, and we can see there where most of the fire activity is taking place. So Eurasia, Canada, parts of the tropics in Mexico and Central America, and elsewhere. And these points are colored according to the value of the FRP. So the darker reds are higher intensity, if you like to think of it that way. This is just a snapshot, and one visualization that we've been running in recent years, which has been very successful, is this animation. So every year we write a summary of wildfire and fire activity around the world for the past 12 months. And this is an article that goes on our website, and one of my colleagues at ECMWF, Sylvie Lamitepo, puts together this animation which shows the daily distribution of fire rated power from the beginning of the year through to the end of the year. So currently now we're into July, and so we see these fires in southern tropical Africa, across Russia, parts of Russia and North America. This is for the full year of 2022. And so it's a very nice animation which shows you the daily changes in the fire locations, and then you can then pick out the seasonality and how that changes around the world throughout the year. So this comes to an end there. So this is at the global scale. There's a lot of different types of vegetation burning, and there's a lot of different trends. I'm not going to go into those in a lot of detail, but I think one of the key features of wildfires in recent years, and Federico also mentioned this, I mean, his presentation was the fires in the Arctic Circle over the last few years. And this is something that we monitored quite closely at the time, and that we continue to monitor every year. So this is just starting with an animation to look at this northern polar projection of fire rated power, similar to the map that I showed previously, but focusing really on these high latitudes. And this is showing the June, July, August totals from 2003 up till 2022. So what it shows is really the location of these fires really moves around a lot from year to year. And that particularly as you focus from now on, you can see that this the north in 2019 and 2020 in particular. And of course, we can break down this information. This is a 20-year data set, and we can break this down into looking then at how fires in this region have changed over time. So we can look at graphs similar to this, which is one way of sort of reformatting the information to try and understand better how the day-to-day fire activity changes, and then also at the seasonal or interannual scale. So at of these three plots, the one on the top left is a daily total of fire rated power for the Arctic Circle, and it's a few years old, but it's showing in red the data from 2020, in gold the data from 2019, and then in the grey bars, which you may be able to make out, is an average of 2003 to 2018. So it gives us immediately some context of those 2 years, how they were relative to each other, and also how they were relative to the years, the previous years in the data set. And we see that 2019 was quite high, but in 2020 it was much higher on a day-to-day basis for certain periods in this summertime period. And then the top right is we have the daily total carbon emissions, and if we look at them in a cumulative way, so adding each day onto the previous days, throughout the whole year, we can see that in 2019 and 2020, again in these red and gold colors, way higher than the previous years where we look at the cumulative emissions. So they were really quite unusual years, and returning back to more what we would consider normal values in 2021 and 2022. And then this is reflected also in the bottom right chart there, which is then the cumulative summertime total estimated carbon emissions for the Arctic Circle, where we can see on a year-by-year basis how those emissions have changed. And again, 2019, 2020 really stand out in this graph, in this chart. So I mentioned, so we can also bring together other data sets. to try and then understand how these fires behave and why they were occurring in this part of the world in this way. So there's no detailed analysis here. This is very simplified, but the argument being that there is, with climate change, the state of the vegetation or the flammability, how ready it is to burn, is changing, and the risk and danger of fire occurring is higher in recent years than it has been in the past. And so those fires in 2019, 2020 were a reflection of this. And here, to kind of illustrate that, where in the shading, where I'm showing anomalies in soil moisture, which is coming from the Copernicus Climate Change Service. Again, this is Earth observation based. It's a long time series of data where we can then identify regions which are drier than what would be climatologically expected. And then overlaid on the shading are the red points, which show the fire observations and their intensity. And what we generally tend to see, and this is showing for the 4-year period, that where the fires are occurring is generally in parts of the parts of the northern hemisphere where there are much drier conditions. And so this is a nice visualization which brings together two independent data sets. The data going into them both does not know about the other product, and so it really shows us that there's a lot of information out there which we can bring together to tell the story and to understand a bit better some of these fire activities. And just to complete the story of the Arctic fires, I mentioned we have this reanalysis, which is a self-consistent 20-year or so data set, which uses the same model system, combines all the observations available over that period, and that allows us to calculate climatology and then also anomalies relative to that climatology. And in this case, I'm showing surface concentration of PM2.5, so it's particulate matter with a mean diameter of less than 2.5 microns. And this is an indicator then of local high air pollution sources. So at the top left is the climatology, and we can see that there's not a lot of darker shading at the highest latitudes and at the continents in the climatology. But then when we look at the anomalies for 2019, 2020, and 2021, we can see the blue colors are negative anomalies, so below the climatological PM2.5, and red high anomalies where it's above that. And certainly you can pick out around parts of Alaska and Canada in 2019, and then in different parts of Siberia, reflecting the distribution of the fire emissions in the other years as well. So again, this is just to kind of complete that picture that we're monitoring wildfires, but we're also monitoring the air quality impacts and aspects of those fires as well. So for the next example, I want to give just a quick overview of some of the visualizations that we provide and have put together for monitoring and doing some communication around the Antarctic ozone hole. So just for a little bit of background, so basically you have the polar vortex that forms during the polar nights. There's no sunlight reaching the pole during the winter, so basically in the months of, I get this right, so through May, June, July, August, which is the austral winter. And you get an accumulation of chlorine-containing compounds in cold conditions. And so when sunlight returns to the high latitudes in the spring, it activates the chemistry, and it's constrained by these strong winds of the polar vortex. And that's kind of illustrated here on the left. This is a visualization that's showing the ozone partial pressure, or essentially the concentration at a particular level of the atmosphere. And it shows how it evolved from August through till the end of, well, through to about mid-December. And so we see at this time, we wait till it comes back to the southern hemisphere. we see that in the early signs of spring, this gradual breakup of the amount of the ozone molecules until by the end of September, there's a very clear hole in the contour, and again, so this is the Antarctic ozone hole. And again, by merging our CAMS data, which is about 20-year record, with ozone data from the C3S era 5 reanalysis, it gives us a 40-year data set of the ozone hole, and then we can understand, and we can, first of all, that the ozone hole is the size and its scale is reducing in accordance with the Montreal protocols and the Montreal Protocol and the changes which are aimed at protecting and repairing the ozone layer. And we can make time series to then look at how our current year is evolving relative to those previous years. And so we have, I should have added the link, but through our website, you can find a page which has all of these monitoring plots. And then from August through till the end of the year of the last few years, you can see a routinely updated picture of the ozone hole evolution relative to the last few years and this longer term climatology. And then one other way of looking at this is to compare all the years together. So this is another animation put together by one of my colleagues at ECMWF, Miha Ratzinger, who also created the previous animation. And then this is looking at the ozone hole evolution for all of the years back to 1979, side by side. So it gives you the sense of how the ozone hole has changed year on year and how it's improving, and how at least the chemical side of things are improving, even though in recent years the dynamics have been quite strong and led to some unusual ozone holes. Okay, so I'm just going to come to a close with just a few minutes on our near real-time monitoring, and by example, I'm going to show the current situation with the wildfires in Canada and the smoke transport. So this is, in a way, if you attended last week's introductory webinar, this is revisiting the last slide that I showed there, but it updated to more recent information. And it's just to make this point that we're doing this in near real time. It's a near real time product, and that these visualizations and the science and the communication that we can do around these events can give some context in a very timely manner to understand how unusual a particular event is and how it's changing. So I'm going to start off with a map of the fire location. So here we're looking at North America, and you can see in the red the fire locations from across British Columbia, Alberta, and Saskatchewan, and also to some degree in Northwest Territories. And then similar to what I showed for the Arctic, we can get a sense of the daily variability, how intense those fires are, or the scale of them relative to what we've seen in previous years, and indeed in terms of the total estimated emissions. So this is just looking at May, and we can see certainly for British Columbia and Saskatchewan, emissions for May up to the 22nd, that's considerably more than what has been experienced in those provinces for the month in the past 20 years or so. And of course, these fires are generating huge amounts of smoke. There's a lot of spectacular visible satellite imagery out there, which has been on social media and shown for the last 2 weeks or so. And of course, that also leads to things like atmospheric pollutants. And here is carbon monoxide, again at 850 hectopascals. And this is the forecast from yesterday. And what it shows is carbon monoxide, the highest values over the fires continuing in Canada, and particularly over large areas of North America, but also transport across the Atlantic, reaching Europe, reaching Scandinavia, and indeed in some cases going up into the Arctic Circle. And so this isn't the latest forecast, but today's forecast shows something very similar. And as those fires continue, it will continue to get this long-range transport, particularly as smoke gets higher into the atmosphere, the winds are stronger and the photochemical lifetime is longer. And really just then to finish is with the analyses in relation to this event. So this is just changing the perspective slightly to look at a more global perspective. These are now analyses of aerosol optical depth, so the amount of aerosol in the atmosphere assimilated into our system to provide these analyses. And then this is every analysis step from the first of, oh, excuse me, maybe, okay, so sorry, this is not the animation I thought it was. So this, again, this is the forecast from yesterday, but this is showing the aerosol optical depth. So again, it shows similar features to what we see with the carbon monoxide. We can see, but we can see additional things with aerosol optical depth, which we don't necessarily have with CO. So particularly if you look over the Mediterranean in this animation, there's desert dust from the Sahara, which is being transported in that direction. But it shows even more so than the complexities of the atmosphere, and having things like carbon monoxide and other pollutants allows us to then disentangle some of the different sources from looking at this. And this is really barely scratching the surface of what we do in CAMS and how we monitor the atmosphere in near real time. But hopefully there's some examples that show you what is possible with this kind of data, and particularly merging satellite data with models to try and squeeze more information out of what's occurring in our atmosphere at the moment. So with that, thank you for your attention and look forward to the discussion.
Okay, thank you, Mark. That was, I mean, great. I think we really had a very nice overview with you and Cathy on the thematic. We are a bit ahead of time, but yeah, I would like to take some questions for now and keep the remaining of them for later, because I would like to give at 3:30 the floor to Simon and Julia. I see that there are questions on practical, technical, and hands-on. There are questions on which data to use. Also questions on Google Earth Engine. So basically one answer fits all. So you will have a data demo from Julia later in 20 minutes. And you will see, a first taste on how to work with the data. For Google Earth Engine, yes, some of them are available on Google Earth Engine. So Sentinel-5P is there, several Sentinel are there, but GE is not the official access. So basically, for instance, if you want to work on visualization, you have also Copernicus Hub. And also concerning which data to use, is a very complex answer. As you have seen, you have several ways, several products, several methods to observe the same phenomenon. So with a different resolution, different geometry, different a different variable, different geophysical variable that is retrieved. So my answer would be you can use a combination of them. So you observe the same thing from different facets. So basically, I would like to start from this question, and know which is the point of view of Cathy and Mark. So on, there are a lot of data, there is a lot of information, what to use for what to use. So how to be guided in terms of usability of the data. I don't know, Mark, Cathy, if you want to comment on this, and then we take a couple of other questions.
Okay, yeah, maybe I can just quickly. So yeah, so maybe I didn't include a link, but through our website we have an online data store which can be accessed by API or by direct download. And so all the data that we provide is of course open access and is available and accessible from there. In terms of the use of access, I work a lot with Federico and with the European Space Agency. We put together a lot of training material over the last 4 or 5 years. And that's all available also through our website, through the EUMETSAT website. And so we're doing what we can to make it easier to use and to access. And I think you'll see from Julia is the kind of tools that are available.
Cathy, do you want to give a comment? I mean, on the question of, okay, there is an enormous amount of data. Yeah. Access and also, I mean, how to choose the data that you would like to use.
How sorry, say the end of what you're saying. How to choose what?
There is one question that I find very interesting, and I think the question is that the number of different satellite programs sources is overwhelming. Can you give or recommend an overview over the available products? I mean, something that probably comment on, put it also in the chat. I mean, a comment on how to navigate in what we have presented today.
Yes, but I don't know. There are different satellites measuring different things. If you take one molecule, for example, carbon monoxide, you can download the data from several satellites, but they don't show exactly the same thing. So depending on what you want, you can study the same event and try to collect all the data you can, either from satellite or ground base or whatever. So, but for example, it depends on the molecule. But not so much carbon monoxide, for example, there's basically YASI and tropomi. And there's also, but less, I see less good. There's some US instrument also. But so it's not so much, it's just the number of data with satellite is overwhelming. That's the thing. So if you focus on one little area, you might have to download the data for a full day, which is overwhelming, of course. But that's the price to pay when you use satellites. It's a lot of data. I saw in the chat that somewhere that shared the map, the ammonia map, and the link is in the chat. So I just sent the YASI website Iris when you can download the YASI data, and also with the map, it was somewhere in the chat also before. So the link was provided.
Okay.
Yeah.
Yeah. I think we can take another question. I think it is also very good for you, Cathy. Is at what height are the particles observed? And we can probably also merge. There is another question somewhere else that is about the concept of the tropospheric column. No.
Okay. Yeah, that's a good question. It depends on the gas you are analyzing. If it's a very weak absorber, then usually basically what we see is a column. It means it's you don't have any information on how is it dispersed into the troposphere. If it's a molecule that has a strong absorption, I mean, for example, carbon monoxide or ozone in this case, we have a guess of the shape of what we call the profile. It means we can guess that it's not the same amount that is located at 3 kilometer altitude and at 10 kilometers, for example. And then if you download the data, you will have a profile instead of a column. So it all depends if the molecule is absorbing strongly or not. Basically, that's an easy answer.
Okay. Mark.
Yeah, maybe I can also comment on it. So, I mean, this is also then obviously an issue for us that we're providing a 3D height and latitude, longitude, atmospheric composition field. And so, but we're assimilating these observations that Cathy described. So we're assimilating something which is a total column or tropospheric column observation. So to get a 3D field, we need to then sort of back engineer it to have some vertical structure as well. Of course, we have a model, which is a 3D model of the atmosphere, and we have some prior knowledge on the emissions, and of course, we have all the meteorology. So we have some kind of a maybe more realistic or a modeled approach to what the vertical structure of the atmosphere is like. But so we can try and get that vertical information out a bit more from the observations we're simulating. But of course, we're having to put the model into the same observation space using which takes into account the fact that it's not a profile, but there's some information on where the information in the observation is coming from.
I take another question and then I would just quickly one question and then go to the next presentations is about the Sentinel-2 for wildfire. So which other satellite data can be used? We try to answer online, but I mean, I just add myself one point. So still talking about Sentinel. So Sentinel-2, we go to Sentinel-3. Yes, you work both, for instance, in the infrared channel. So in the infrared, you can observe the fire pixels with the fire radiative power. So seeing how much fire is emitting in the infrared. But you also have the visible channels with the composition of RGB, identifying, for instance, the plumes, as we have seen for FCI. FCI, for instance, does a little bit of the same thing. So uses channels that are in 10.7, 10.8 micrometers. So going in the infrared, and then joining with the visible channels, with the composition of the visible channels to enhance, let's say, the brown signal of the plumes. In addition, you have the pollutants, so the like CO, like NO2, that are in general observed in the infrared part of the spectrum. So, I mean, the question that is not complete, but you really have, I mean, you really can make use of the whole observed spectrum to detect wildfire relevant variables. But I mean, if you want to have additional items, or if you have more specific questions, just reply and we try to go there. So I suggested that we move to the next two presentations, and then we finish the questions online or offline. So we can also put answer to the questions in Slido. So I invite you, Mark, Cathy, and Simon, and Julia, if you wish to do so, in order that that if you cannot answer here live, we answer offline. So I introduce you Simon Prout. From the National Centre for Earth Observation, senior scientist from the UK. Please, Simon, the floor is yours.
Great. Well, thank you very much for the introduction. I've just started sharing my slides now, so hopefully you can see those.
Perfectly. Go.
Great. So I was asked to talk a bit about volcanic eruptions and dust, which are linked quite closely to my research. I do a lot of research on severe weather, and these feed into that a lot. Especially dust is also linked to thunderstorms and things like that. And I've actually done my presentation in a slightly different way to the others, in that I'm going to give a few examples of interesting events that I have seen and give some thoughts about how I visualize those and some challenges I faced along the way. So I'll start off with the volcanoes. And in some cases, volcanoes are actually very easy to tell a story with Earth observation data. This is an example of the Anak Krakatau volcano in Indonesia, I think it is. You can see it there on the right-hand side in the middle of an eruption. This image is from Sentinel-2, and I got it from Brockman Consultants. You can see a nice plume coming off there. There's a lot of ash and cloud in there. It's this kind of brown color due to the ash. And one thing I found very interesting here is that the island, the volcano itself, is a different color to the other volcanoes nearby. And that's because it's quite newly formed. So the eruption itself built up the land until it came above the ocean. And it's not yet had time for plants and other types of vegetation to grow there. So it's still this kind of raw lava color compared to the other islands. And when you get a volcano like this, it's incredibly easy to produce absolutely stunning visuals with Copernicus or other sorts of data. And I've got a few links on the left-hand side of the screen to where you can do this with not really any knowledge of programming or tools like that. You can just log into these websites and get started. So the first one is for Copernicus data, so Sentinels 2, 3, 5, and it also contains some other satellites like Landsat. The next link, which is called Worldview, contains a lot of data from American satellites, so the NASA ones, and also from NOAA, which is their kind of weather agency. Lastly, something I'll talk about a lot in my slides is geostationary weather satellite data. Federico already kind of introduced this, so these satellites that sit in a fixed point above the Earth and just look at a given region all the time. And the last link you see goes to a provider where they show these geostationary images, and you can animate them, zoom in, change what you're looking at, things like that. So it's well worth just going into those and having a play around. So that's a very easy example. Another fairly easy eruption to to visualize was Hungatunga, which most of you probably remember from January of last year. I did some research on this one and found that it was actually the tallest eruption ever recorded. So the cloud that you see in the satellite data here reached almost 60 kilometers above the Earth, just more than halfway into space. So it's a really massive eruption, and the shockwave from it was felt around the world in little wiggles on pressure readings at weather stations and things like that. So in one way, this satellite data tells its own story. You can really see the violence of the eruption here. And this is geostationary data from a Japanese satellite called Himawari. So this satellite, Himawari, covers the Western Pacific, Southeast Asia, Australia, up to Japan and Kamchatka, where there's also a lot of volcanoes. We also have GOES, which are American satellites, covering the Eastern Pacific and also North and South America. And then, of course, we have the EUMETSAT satellites, MEEO second generation at the moment, covering Europe, Africa, and going over into the Middle East and towards India. And soon we'll have this amazing MEEO third generation, which will provide excellent quality animations and images, a bit like this, but hopefully not with quite so many volcanoes near us here in Europe. But one thing you will notice in this video is that it gets dark towards the end, which is the sun setting. And that's one of the big problems with volcanoes. They tend to go off whenever they want. They don't go off in the afternoon or the morning. They can happen any time of day. So as well as these true color images, which show reflected sunlight, it's also really useful to be able to look in the infrared. So here is the same animation to begin with, but now also using infrared data, so temperature data at night. And this shows the eruption, and it shows another separate eruption actually as well. You could just see it there. I'll let it play again. So you miss it in the visible data, but the infrared shows a secondary eruption, which, even though much smaller than the first, here it goes, was still one of the biggest eruptions of 2022. You can also see this kind of gray colored cloud that drifts over towards the left. And that's a lot of volcanic ash. Eventually that passed over Australia and across the Indian Ocean towards Africa as well. And it produced a lot of amazing colored sunsets in northern Australia. So meteorologists on TV and things were using a lot of this data from Himawari and other satellites to show how this ash moved and where people could see it and why the sky might be hazy, things like that. So sometimes you need to use this infrared data. It's a little bit harder to visualize simply because it's not something we're used to seeing with the human eye, but it can highlight both unseen events and allow us to see at night. So I think it's always worth experimenting with different combinations of data, combining day and night, or sometimes just using this infrared data on its own to see what it shows, as the most obvious combinations of data may not be the best. Getting into a bit more detail, we can use the Copernicus Sentinel satellites, especially Sentinel-2, to really zoom in on areas affected by volcanoes. And this is an eruption from a couple of years ago in the Canary Islands, I think it was. And here you can very clearly see the lava in this Sentinel-2 image flowing from the volcano down into the ocean. And this is actually, even though it looks like something the human eye would see, it still involves infrared data. As the lava was below cloud, you can see a bit of the cloud over on the right-hand side. And because there was this cloud cover, it was very difficult to visualize the lava without putting in some of this infrared signal. And when you put the temperature in, the lava pops through the cloud a little bit and you can visualize it really clearly like this. And I think the geostationary data that I showed before is very good for giving a sense of scale. It shows how big an eruption is, how powerful it is, how fast it occurs. But this is much better for providing a bit more of a human context. As hopefully you can see it here, but if not, all the slides will be available later. So you'll be able to zoom in and you'll be able to see farmland, houses, roads. So it puts it a bit more on a scale that people can understand and really gives you the sense of destruction that these things could cause. But satellites can also show us things that the human eye can't see, such as sulfur dioxide. We've already heard a lot in Cathy and Mark's presentations about the various gases in the atmosphere, and we can visualize those with satellites as well. And sulfur dioxide is produced a lot by volcanoes, along with ash and things like that. But it's in some ways much easier to visualize than ash. In this example, which is a volcano in Kamchatka that erupted last month, the ash was hidden in cloud, so you couldn't see it. But the SO2 is this kind of orange and red colored blob you see traveling from left to right, and that shows up really clearly. And ash is important because it can affect flights. As any of us who were around in Europe in 2010 will probably remember the Eyjafjallajökull eruption, which cancelled flights for many days. So it's useful to be able to see ash. It's also useful to have proxies, things like SO2, sulfur dioxide, that you can use when you can't see the ash, just to show how all the stuff from the volcano is moving. And this is quite a good example, as it shows all the SO2 and, by proxy, the ash moving towards North America, which ended up in a few cancelled flights in Alaska and northern Canada. Luckily, it passed over quite an empty area without too much population or too many flights going around. So this is another example of how it's always useful to look beyond the standard true color or just one temperature channel images from geostationary satellites. Here I'm combining two different channels, and putting those together really highlights where this SO2 is. So now we'll move on to dust storms, which is, I think, one of the most challenging things to visualize. So thank you very much to the organizers for giving me this one to talk about. It's always good to have a bit of a challenge like this. But I thought I'd start off with something nice and easy. As here we see a plume of dust coming off West Africa and heading again towards the Canary Islands. So not only do the Canary Islands have volcanoes, they also have dust. So quite a few challenges to face if you're living around there. And when the dust is over the ocean, you can see it very clearly. So this area here, I don't know if you can see my mouse pointer, but if you can, there's quite a bright area over the ocean, which is the dust coming off West Africa. But what you can't see is the dust over the land itself. As this dust is still blowing, it doesn't start at the coastline. It's blowing over West Africa itself on the right-hand side of the image. You just can't see it very clearly because you've got a kind of yellow-colored layer of dust over a yellow-colored layer of ground. So you need to kind of think outside the box a little bit about how best to visualize that. So to illustrate that, I thought I'd use an example from the Middle East last year, a huge set of dust storms that passed through Iraq, Saudi Arabia, and other Middle Eastern countries pretty much a year ago. And this was a very significant dust storm because, as you can see in this picture from Reuters, which is in Baghdad, the visibility was very low. You couldn't see more than a couple of 100 meters. In some places, you couldn't see more than 50 meters. A lot of flights were cancelled as a result. There were more traffic accidents because people couldn't see properly when they were driving. And there were also a lot of respiratory problems from breathing in this dust for days and days. But when you try to visualize this with satellite data, some of the satellites didn't really show it very well at all. And others, such as, unfortunately, in this case, Copernicus Sentinel-3, had some problems with where the line between different satellites was, as the satellites only scan a fairly narrow part of the globe at any one time. And we were unlucky on these days that where the dust storm was in the join between two scans. So if you look on the right-hand side, you can see a very bright layer of dust. And then on the left, it's a bit harder to pick up where the dust was in the satellite image from about an hour and a half later. And that's simply because the dust moved, the sun moved, and it's not such a good way to visualize it. So in some cases, it's always worth checking out things. This is from Sentinel Hub. In some cases, you get a very clear image of the dust. And in other cases, like here, you can see it, but it's maybe not an ideal image. So you can again turn to the geostationary data to provide a bit of a different perspective. And here I'm showing what's called a dust RGB. So this is from EUMETSAT's MEEOsat second generation, which provides data every 15 minutes over the Middle East and India, places like that. And it's this purple color because we're using various infrared bands, which are designed to highlight where dust is. And you can probably also see a number of little dots scattered around the image. Most of them are green here. These are weather stations at airports. So I've combined satellite data with weather station data. And the point of this weather station data is that at airports, visibility is key because you can't land, you can't take off if visibility is too low. So by measuring how far you can see at airports and putting that on the map, it helps show where the dust is. So the dust will start in the upper left of the image, so towards Syria and Israel, these types of places along the Mediterranean coast. So I'll start the animation, and you should see the dust moving, and these green dots turn yellow orange and red as the visibility gets worse. And these dust storms are actually triggered by thunderstorms. You can see them now. You can see the dust showing up a little bit as this kind of pink color moving towards the right. And now it goes a kind of dark purple as it crosses Iraq. And you can see these dots changing to red and orange as the dust makes the visibility very bad, now passing through Saudi Arabia. It gets a little bit harder to see with the satellite now because the dust is spreading out over a wide area, but you can still see it with these ground-based airport measurements. So combining the satellite data with airport visibility data provides an extra bit of context and also helps focus in on a few of the key areas. Like you could see, I won't let it start again, but up in Iraq, you could see some going really red colors, which indicates visibility of less than 50 meters. So it's a really severe event, and this kind of helps highlight that. You can also use Copernicus satellites to illustrate the dust in a different way. It's sometimes hard to get your head around just how severe these dust events are, as unless you've experienced one, it's quite hard to understand the context. So one way to show that is a kind of before and after of what happens when dust storm passes through. So this is a place in West Africa, it frequently experiences severe dust storms. This is quite close to the border with Mali, Senegal, that kind of area experiences a lot of dust storms. And this is before a large dust event. And this is the same region during the dust event. And if I flick backwards and forwards between these two, you can see very clearly the ground just disappears. You can't see it anymore. And this is looking down from space, where we have a view of just a thin layer of dust. Whereas if you're actually sitting in it, you're looking through all this dust and the visibility is even worse. So sometimes these before and after images can provide a lot of good context as to what we're seeing. So I thought I'd finish up with a few concluding thoughts on the examples I've shown. I think visible data, these true color images, I showed a few of them, are very useful. They're great. They provide beautiful imagery and have the advantage that they look very much what the human eye would see, which makes it easy for people to understand. But sometimes they're not the most suitable type of image. So trying infrared data, like for the sulfur dioxide or like for the dust, allows you to see things that you can't otherwise see, which can be very useful if you want to tell a certain story about ash moving across flight routes, things like that. Combining Earth observation data with other sources of data, such as airport visibility data, or for volcanoes, for example, seismograph data, as you get these little wiggles and jumps, cause mini earthquakes, I guess you could call them, when a volcano goes off. And so you could do something very similar to my dust example by doing seismographs in the region around a volcano and showing how the shock waves spread out from it. I think a few people did that with the Hungatunga eruption, for example. So Earth observation data is great, but sometimes it's even better when you combine it with other sources of data. You can also try quite a wide variety of different satellites. I know this event is mainly about Copernicus and EUMETSAT data, but we shouldn't forget the Japanese and American satellites I talked about, and also things like the MODIS sensor and VIIRS, which provide very similar capabilities to the Copernicus sensors. And by combining them all, you can sometimes see things one satellite would miss and another picks up very nicely. The geostationary weather satellites might not be able to provide the same level of detail as Copernicus, but they can produce these nice animations, which are very useful for showing how events change, volcanic eruptions, how they evolve, how dust moves. And also, I think in a couple of weeks' time, you'll hear about severe weather, how you can visualize severe weather. Geostationary satellites are absolutely perfect for doing that as well. Lastly, I thought I'd finish by saying that working with this type of data isn't always easy, especially if you're in a rush or you're on a deadline or you've not worked with it before. But I think the Earth observation community is very open. There's a lot of us on Twitter, for example. Jonathan Amos said it last week, you can always come and talk to us. You learn who the experts are, you learn who knows about which type of different data, and you can always ask for help or advice. And we're usually pretty happy to give that, as depending on time, we're happy to help. And you should always not be afraid of asking us. So on that note, I'll finish talking and thank you very much for listening to me.
Thank you, Simon. That was just great. I think, you really told us a very nice story and provided us very, very clear examples on what we are, trying to say. So the combination of the data, the combination of geometry, the combination of techniques. That, as you said, is not easy. So when you see an image, you say, "Oh, whoa, that's that's that straightforward." But what you have behind is very, very complex, but also really, really important, really interesting. Thank you very much. I keep you on hold because there will be questions for you, but I want to conclude the presentation with Julia. Hi, Julia. And Julia will provide you some elements on the data access, on the data usage. So Julia will answer directly to one of the questions that we have. You will say in 15 minutes, Julia, right? Is that possible?
Yes, I can also maybe make it shorter because I made a summary slides of the most important links and parts.
Perfect. Because there are many questions, and we would like to also to give floor of 10 minutes of question and answer. The floor is yours.
Okay,
please.
Thank you. Thanks, Federico. So I'll start sharing my screen. And could I just get a confirmation that you see my slides? Yes, okay, thank you. Okay, so hello from my side. So I'll try to be quite practical, so and also stay in the foreseen time. So the next 5 to 7 minutes, I try to give you a short overview of some resources you can use and leverage to access the data, get an overview to the data, and that hopefully also give you some practical examples how to visualize the data that has been presented by the previous speakers. So I'll go quite fast in the first slide. So we have like several application domains. Like one is wildfires, as I said already, and the other one is dust monitoring. For wildfires, we had recent examples, as the previous speakers also said, wildfires in Siberia and Alberta. Here are just 2 examples from Copernicus data, how we can monitor wildfires. So one is from the Sentinel-3 SLSTR instrument for the wildfires in Siberia, and here we also have from Sentinel-3, but from the other instrument from OLCI, level 1B RGB composite on 7th of May 2023. We also published a case study specifically highlighting these wildfires. So if you're interested, you see here the QR code. It has been published on the 11th of May and analyzing a bit more in detail specifically these fires. Dust storms, as also Simon mentioned, is another application case study. And here we just had, this is an animation from Mark on 11th of May, so like 1.5 weeks ago, that in fact predicted Saharan dust coming towards southern Italy and southern Europe. This is an example from the CAMS dust forecast. And then on the right, we have Sentinel-5P Tropomi data. This is for an event at the beginning of April, where there were quite a bit of Saharan dust transported over the Canary Islands and over the northeastern African coast. And so this is the level 2 ultraviolet index product from Sentinel-5P. So I think there's a lot of comments also on the chat there. So the question is, okay, there's a lot of products there, but how can you access them, and how can you maybe also replicate and reproduce these examples? You saw them. And since 2019, for EUMETSAT, I've been involved in developing specifically training modules and practical examples to make it easier to use and access data for atmospheric composition and specifically satellite data. And so in the next set of slides, I will just show you some of the resources you can use to work with different data access systems on accessing the data, but also on visualizing the data. So we developed specifically on wildfires and on dust 2 thematic modules, and the idea of thematic modules is to provide you for a specific application area quite holistic and comprehensive overview of different data sets you can use, and also it gives you a better understanding and help to interpret the data. So to also better understand what you can use some of the data and where are also the limitations. And the specific or particular asset here on these thematic modules is that you have a browsable website on the front end, so you can easily just browse through it. If you go to fire.trainhub.eumetsat.in, for example, so, oh, sorry, I can also see here. So you have on here just a website, and you can browse through the content, and it gives you a really nice background information on dust monitoring with satellite images and ground-based data and model data. And then you get a specific introduction to different data sets from satellites, from ground-based information, and also from models. And then for each of the data sets, you get an introduction of what the data is about, some basic facts, and also practical examples, how you can access the data. So whether it is for download, or if it is also possible to use a programmatic access or an API. And then you have here a specific overview, or like in detailed step-by-step guide on how, once you download the data, how you can read the data in with Python, and then at the end how you can also visualize it. So this is now for ground-based information, but here we have an example, for example, for Sentinel-5P, Tropomi, ultraviolet index, if this is okay. This doesn't or maybe here for why doesn't this, okay, the internet seems to be, so here is for the GOM2 absorbing aerosol index product, and this is the same structure. So you get then here a very practical introduction on it. The same style, or a similar setup we also have for the wildfire book. So this features 2 different case studies on California in the US, and 1 case study on the Mediterranean in 2021. And this highlights specific different data sets you can use to forecast and assess the pre-fire risk, then to monitor active fires, and also to assess post-fire impact. So you have quite an overview of different data sets, understanding for which you specifically can use and utilize the data that are introduced. So the specific, or the particular thing or highlight for here is also that we have on the front end here the website, and then each notebook you can also access as an executable notebook. So so if you go, so each notebook you can also access on a Jupyter Hub, and you have the login details on the website. So if you would like to work directly with the data and with the example, or you want to modify it with some other data, you have not only the website, but also in the back end the Jupyter Hub, where you can execute the notebooks. So I go here, and here you see the slides, and you also have QR codes to it. Here's just an overview of these thematic modules. I'll jump over here. Another resource that might be helpful is EUMETSAT Train Hub platform, and this is currently in development. It will soon be available under trainhub.eumetsat.int. So please watch out. For now, you will find it under this link here. So, and it will give you on different application areas, not only atmosphere, but also climate and marine and other application areas from Copernicus, training resources. And the highlight here is that for each of the application areas like atmosphere here, you see then a full set of notebooks available. And for example, for atmosphere, we developed a training course with more than 50 notebooks highlighting different satellite data for atmospheric composition. And then you can also have the search functionalities on the left where you can look for notebooks highlighting a specific sensor, a specific satellite, and or specific variables. Like if you're interested in an example with ammonia data, for example, then you can also look for training resources available here via a search functionality. And then, so this is how it looks like. So once, so you have here the overview, the specific highlight here is that like for each notebooks, you also see a rendered version and you can browse through it. But you have at the same time also a link that allows you to open it via a Jupyter Hub instance that allows you to execute a notebook and directly access the data, or you can also open it or see the notebook and clone it from GitLab. So you will have here all the links available that help you to access and run the code we show you here. Good. So then a similar notebook portal is also available via Wikio. So here is the link to the Wikio notebook portal. For all the data that are available on Wikio for atmosphere, climate, land, machine learning, marine applications, you also have notebooks. And so feel free to browse and you see then specific notebooks. And in the back end, you have then the notebooks available on the Jupyter Hub instance from Wikio. And Wikio is the cloud processing facility from Copernicus. And here, just to conclude my short presentation, overview of all the training resources, specifically for Copernicus atmosphere applications coming from EUMETSAT and ECMWF. So as I said, please have a look to the notebook portals, the EUMETSAT Train Hub and the Wikio notebook portal, then the thematic application modules and on dust and fire applications. And then we have, as I said, also specific learning content for different satellite and model-based data. So there's we call it LTPY, the learning tool for Python on atmospheric composition, which has more than 50 notebooks on satellite atmospheric composition data. Then there's Wikio for atmosphere, so specific atmosphere applications on Wikio, and there are 2 examples on fire and air quality are available here, like on GitHub. And then there's also data tutorials from the Copernicus Atmosphere Monitoring Service available also as a Jupyter book, and I linked here, or I provided a link here. And with this, I thank you and feel free to also reach out if you have further questions. Thank you.
Thank you very much, Julia, also for being on time. These are a lot of resources, so please browse them. And I mean, we cannot do everything today, so present, introduce the resources, make a full demo, but come back to us. So as Simon said, we are a very friendly community of guys, of people, and we are really open. We have training resources, support that goes from the social to the Git to the courses. So please follow us, and I mean, there are many ways and many possibilities to support you. Thanks again, Julia. Thanks again to Cathy, Mark, and Simon for the presentation. I would probably keep other 10 minutes, 5 to 10 minutes to tackle some other questions. Probably closing at 4:20. I see that the number of participants is going down. It is fully understandable. But yeah, let's try to tackle some questions. So, for instance, we can take one on the process for the data myself and learn how to build similar fire detecting models. Can you recommend sources for the learning of the methods? Yes. I mean, as you have seen, Julia has presented these Jupyter resources. I don't know if you want to say something more, Julia, on this, on the training resources for working with the wildfire data, or also Mark, you want to comment this? Hello?
Yeah, regarding training resources for wildfires.
Yeah.
As I said, I think as a good start would be the thematic module we developed. So the thematic module has a specific focus on how we can use current data in preparation for upcoming satellites, but this will give you already also a good indication what is coming in the next years. So if you go to dust.trainhub.eumetsat.int, I think this will give you a really nice overview from pre-fires, active fires, but also post-fire assessment. And there's also a lot of valuable links that link you to other and further resources. Otherwise, there's also, we had some short courses like from EUMETSAT on wildfires, and so there's also, you can, if you go to the training site from EUMETSAT, there's also in the past some short courses on wildfires, which might be helpful.
Okay, can you drop on the chat the links, Julia, when tackle the next question? Okay. Stop here. Okay, stop. There is a question from Cathy. I mean, there are two questions for Cathy. I don't know if Cathy, if you're still around, about ammonia. So the first one is from Alexander about the comparison of the amount of ammonia that comes from different sources. This is the case of fertilizers versus cows. And also there is another question on ammonia that I have. I keep track of it, and was about the, let's say, the number of days or the possibility. I mean, how high how resolved in time I can go. So basically the question was how much time is accumulated and how.
Okay. So yes.
That's fine.
Okay. So the price to pay for satellite data is that you have 1 or 2 overpass per day. And on top of that, this overpass, what you see at the same time, what we call the pixel on the ground, it means it's the amount of the Earth you are measuring. It's quite large. So if you want to focus on a single industry or a single field, it's not very easy with one overpass. You can do that if you average over months, or even easier if you average over years. And then we have also a special processing, and then we can like try to go down and have a better resolved data. But for that, you have to accumulate for days and days, I would say. So if the source is changing rapidly, it's not easy. If the source is small and changes rapidly, it's not easy to track. If you want to track, for example, I don't know, animals that are moving away, it's not easy. If there are always animals coming at the same area, doing and stay for a long time, then you can track the source. So it's a question of error in the data. The more you accumulate the data, the less error you have. But that's okay.
Okay. Okay, there is a question on CO2. So to observe the CO2 absorption from plants. I mean, we haven't mentioned CO2 today. But yes, I don't know if you want to comment. I mean, I can provide the first hint. Yes, we can observe
Okay.
CO2 from satellite, but yeah, please, Cathy.
I can give a very quick comment on CO2. CO2 is hard to measure from space because CO2 has a very long lifetime. It means when it is emitted by any source, like traffic, volcano, anything you can see, anything that is burning, then it stays in the atmosphere for years and years. In fact, approximately 100 years. So that means it's mixed everywhere. So there is CO2 everywhere. So it's hard to distinguish any single source of CO2. But there are some satellites that start to do it, but it's not easy. So it's much more tricky to measure CO2 from space than what we just showed for dust, ammonia, or CO. So CO2 is trickier to measure from space. So luckily we have some ground-based station. But in the future, there's this Sentinel-7. It might, in fact, provide very relevant data to increase the monitoring of CO2.
Yes, okay. There is also a question that is a bit above. This is for Mark. Detecting or monitoring or tracking wildfires from CAMS using CO or EOD. So there is the question is for CAMS, what are the advantage or disadvantage of following fires using EOD, organic matter, or instead of CO?
Yeah, so yeah, thanks for the question. So I tried to answer it briefly within the character limit of Slido, but maybe just to reiterate. So yeah, so I think for the first quick look, I usually use AOD because it's a 2D field. It's quite lightweight for downloading from our data store and being able to quickly make animations and maps. Industrial and road traffic sources as well as fires, but when there's a fire, it's considerably more. And then for more detailed analysis to look at vertical distributions and this kind of thing, then something like carbon monoxide or anything with a mixing ratio. So indeed, organic matter aerosol mixing ratio can be used to then look at different height levels or to get the vertical distribution to see how high up in the atmosphere it's going, and you can track that. But like I said, the further away you are from the fires, the more likely is the plume is higher up in the atmosphere. So I think those are the sort of main thinking behind choosing a parameter to look at.
Okay. There is a question on. I mean, is a YASI, but I think this question is open. I mean, it's not only YASI, sensitive enough to, I mean, to detect small or local sources of fire. And this is, I mean, this is a reference to human impact, no, like burned villages in Myanmar. But I mean, we can also think of, let's say, less tragic or less difficult situation. So I would reformulate the question. So. Are we able to, I mean, to detect really at the village or the human ecumene or human ensemble scale? This is also a question for Simon. So anyone else? I asked for human right research work. Yes, I mean, we can apply to this. So the capability to detect a different type of events. Simon, I don't know if you want to comment on this. So to the capability to use the satellite to monitor also, let's say, this type of events or.
It's a very good question. That I think the pixel size is very large, so it probably can't see these small fires and events. But other satellites like Sentinel-3 has a sensor called SLSTR, which would be much better suited to detecting these fires. As an aside, since the Ukraine war started, I've actually been working on using MEEOsat data to detect, let's call them events that happen in Ukraine and areas around there in what's called the rapid scan that produces data every 5 minutes. So by looking for very sudden changes, flashes in the fire channel for MEEOsat at 3.9 microns. When that suddenly changes, you know something has happened on the ground, which can be a wildfire, or in the case of Ukraine, is more likely to be something to do with the ongoing war. So even these quite coarse resolution satellites like MEEOsat, which is supposed to have a 3-kilometer pixel size, can still detect very small events happening. So I think it depends a lot on the context of where you're looking and what you want to see. But yes, definitely, you can see human-induced things related also to human rights, wars, all that kind of thing. Yes.
I can probably add one point. No, so you, in fact, also the MEEOsat third generation. I mean, I have shown that you have 1 kilometer resolution. So it's a very technical answer, but I mean, basically, these what Simon just said are signatures that can be observed from satellite. Of course, you really need the knowledge that Simon has, no? So to identify these events from background or from other potential signals. But yes, the potential of usage is very high. I can just mention another places, no? Another place of the world where there is some relevance, and is, for instance, the impact of fire in Amazonia region. That are that the combination of Earth observation data where are really used to detect the changes in vegetation and also the daily activity of human-induced fires in order to manage and to change the usage of the terrain in the forest. So yes, you should really use the cum grano salis. No, you should be really make an advanced use. But yes, there are many perspectives on this. I think we can go to, I mean, there was another, I mean, there are many good questions, I should say. There was another one on how to distinguish between cloud and fires, because I mean, the question is they may have the same signature, and maybe Simon wants to give a hint of this. And then there is another one on atmospheric rivers, and through atmospheric rivers are not precisely atmospheric composition, but it's quite interesting. So atmospheric rivers and water vapor. So Simon, I don't know if you want to comment on I mean, how to discriminate between a cloud and the smoke.
Yeah, I saw that question, and I was thinking that's a very difficult one to answer.
Yes, because we do this daily, and there are tons of papers now for
exactly
comment on this. But I mean,
so yeah, it's really difficult because they're a similar color. They both look kind of white. Smoke can take on other colors, of course. It can be more black or gray. So that's one way to distinguish it using the true color data. Another way is the shape of it, as clouds tend to be a kind of semi-random type shape, let's say very fluffy around the edges or something, whereas smoke plumes tend to come from one source, so they're quite often a triangular shape instead. So by looking at the shape of them, you can distinguish them. But quite often using the geostationary data, if you animate it, it will also look very different to a regular cloud. It'll spread out much more, it won't grow or dissipate, it'll move in one direction with the wind. So there's no one way of telling smoke and cloud apart, but just by looking at a few different examples, you can quite often figure it out.
Yes. Okay. Thanks. And about atmospheric rivers, so there is also another question on how to monitor water vapor, and there is also a related question to atmospheric rivers that we can tackle. I don't know if you want to comment, Simon or Cathy or whoever.
Yeah, sorry, I really have to go now.
Yeah,
Okay?
sure, no
Yeah,
problem.
okay, bye.
So thank you very much, Cathy, for joining. That was great. Yes. I don't know, Simon, if you want to comment, or I can do this.
It's a bit out of my expertise, but using water vapor channels that are sensitive to water vapor at different altitudes in the atmosphere, you can detect atmospheric rivers to some extent with that. But yeah, like I say, it's a bit out of my expertise, so it's probably worth reading a bit more about that.
Yeah. No, I mean, my point is that water vapor is the first, is the main target. I mean, you can see the changes in terms of concentration of water vapor, and water vapor can be measured, for instance, in the infrared, but by different satellites. So you can measure it also in the microwaves, no? So you can measure it by Meteosat, but also by the polar satellites. It is open, I mean, another Pandora vase, but yes, again, the question is, the answer is always the same. So you have different ranges. So where water vapor is active in terms of radiative transfer, and is active in different spectral ranges. So in T spectral ranges, you can measure water vapor, and you can detect atmospheric rivers on geostationary. I will try to put in an example, a story, a EUMETSAT story on atmospheric rivers in the chat in a minute. Okay, I think we are really a bit ahead of schedule, so I propose that we close the Q&A, unless if you want to, or Simon, Mark, Julia, you want to answer to one specific question that you really see as a burning one, or a very exciting, but if not, otherwise I would go toward the end and thank I think Julia and Cathy that are now in other meetings. So thanks to them, and also thanks to you, to Simon and to Mark for joining. That was, I think that was very exciting. There are already many proposals and ideas in the chat saying, okay, please, can you redo it or do this and that? We will do. I mean, it's a user request that we are happy to tackle, and thanks especially to all the audience and all the participants. So it was absolutely great to be with you this afternoon. We were a big group, even if we were in a virtual configuration, but that was really a pleasure. And also a big thanks to all the organizers of the workshop, to the Copernicus program, and to all our colleagues, my colleagues that have been made it possible. Thank you very much. Have a very good afternoon, and see you around. And also in particular, if you are interested, see you in the next workshop of the series. That will be, I think, if I remember well, next week. Thank you very much. Thanks again, everybody. People who has made a talk, who has provided questions. Every question is good. And see you soon, and have a nice afternoon. Bye-bye.
Thanks, bye.